Okay. Um, we were discussing how the S band, width of the S band changes when you change the lattice parameter. The spacing between the atoms is changed, and so it is very simple to understand. When you have when the distance between two atoms is less, the overlap between orbitals is good, and so bonding orbital and anti-bonding orbital, most bonding, most anti-bonding, they are well separated by a huge, so energy difference is, gap is, so energy, if you look at the energy between these two is, so you have maximum separation between top of the valence band, top of the band and bottom of the band. However, and intervening you have different combinations. Thank you. Thank you. Thank you. Huh. So, so top of the valence band, so top of the band, not just, I'm not talking about, so this is the top of the band for this, when A is equal to 1 angstrom, and this is, here is the bottom. So this is the separation. So simple understanding of a molecular orbital theory, the way we have understood, that explains this thing, that good interaction, wider separation. Slightly, when the separation between atoms is changed, then the energy levels of this, the interaction between the atom orbitals is poor, and so the drop in energy for the bonding molecular orbital and the most anti-bonding orbital is less, and so overall width is less, width of the band. So width of the band is the separation between bottom and the top of the band. So this goes on decreasing when you have A is equal to 3 angstrom. Okay. So this is the list. So this is defined as, okay, yeah. So this, how do we, so this is related to the anti-bonding orbitals that increased in energy. Okay. So which also means that the bandwidth increases. So we say that the bandwidth has increased when the distance between the atoms is reduced, or the unit cell A, unit cell constant, the A is reduced, and so the electron mobility will increase within the band. Uh, so this is called wide band, good orbital overlap, and high carrier mobility is obtained in this kind of bands. So we also call it flat band, where you have the distance between the atoms is uh, greater, 300 picometers, width is less. So because of the width, the name has been given depending on the width of the band. Where the width is large, it is called dispersive band, and when the width is less, we call it uh, flat band, flat. Okay. So this is the understanding we have developed, assuming the hydrogen atoms, you have one dimensional lattice, this kind of lattice. Okay. Okay. So this kind of, then I also told you that in the same way, the way we have done for s orbitals, we can combine p orbitals, and in that case you can again construct the orbitals most bonding. The most bonding orbital here would be this, uh, when the constructive interference is happening in all of them, and this is the most uh, anti-bonding orbital, where each one of the next orbital placed is having destructive interference between them. So this kind of plot, here you will find that orbitals which are having different symmetry. So one p orbital has both plus and minus lobes, sine of wave function. So in these cases you have k is equal to 0 for the most anti-bonding orbital, and most bonding orbital has pi by a, the k value is pi by a. So momentum k is also, the wave vector is in a crystal lattice. We also called it, it denotes the momentum of the crystal, the wave that is formed, the electron's momentum. Okay, so momentum in this orbital is k is 0, means momentum is 0. Okay, so in general the plots will be like this. For S, you have this like so the most bonding is here at 0 value of pi by k, and this is at pi by 2. So plus pi by a, you have this one. And p orbital, when you are taking pz orbital, it is reversed again. So you can see G-rayed orbital, s orbital, when you the atomic orbitals that you are taking, if that is G-rayed, un-G-rayed, then the profile is different like this. So S, P, D and F. So if you draw the complete profile, you will draw another parabola here, a reverse parabola on this side like this. So this kind of orbitals, this kind of band, S band, P band, D band, F band. So considering their interaction along the internuclear axis, that is how it is obtained. And then another point is that all these bands which are formed due to interaction with the valence shell orbitals, they are called valence bands. Then you can also have interaction of the core orbitals, जो inner shell orbitals हैं, उसका भी इंटरेक्शन होगा, उसके भी जैसे कि एल्यूमिनियम, मैग्नीशियम, सोडियम, इसका कंसिडर करें तो 1s, 2s, 2p. So band 1s band, 2s band, 2p band, and then this is the valence shell, and the orbitals overlap in the crystal along all, and when they so these are filled core levels. So these are core bands. Okay, you will also note that the interaction inner core orbitals, जो अंदर वाले orbitals हैं, उनका interaction अच्छा नहीं होगा. They will be they are withdrawn inwards. तो overlap उनके बीच का जो actual जो distance है, overlap approach अच्छा से नहीं होगा. Overlap will not be good. So width of the band will be less. अभी आपने देखा जब separation बढ़ाते हैं, overlap अच्छा नहीं होता है orbitals का, तो width of the band will be less. So if you compare the S band 1s, so sorry 1s band, उसका width सबसे कम होगा, फिर 2s का थोड़ा सा ज़्यादा, 3s का और भी ज़्यादा होगा. अगर इंडिविजुअली 3 S बैंड हम देखें, 1s, 2s, 3s, 3s इज द वैलेंस शेल. सो वैलेंस वाला वो बाहर की तरफ है, इट इज सो दूसरा जो एटम आएगा उसके साथ उसके जो 3s ऑर्बिटल होगा उसके साथ ओवरलैप बेटर होगा. सो दैट इज गिविंग यू वाइडर बैंड. यहाँ पे 3s और 3p का ओवरलैप हो जा रहा है, इसलिए ऐसा दिखाया गया है. Actually this is what happens. So filled core levels, they do not interact strongly because of because they are drawn inwards, they are more closer to the nucleus. So because of poor overlap, their width will be less and narrow bands will be obtained. Okay, but they will be well separated in terms of energy. Less width but well separated amongst themselves. Okay, whereas the in the valence shell what we observe, 3s 3p width ज़्यादा होगा. तो width अगर ज़्यादा होगा तो 3p का बैंड जो बनेगा वो नीचे की तरफ स्प्रेड होगा, 3s वाला भी थोड़ा ऊपर जाएगा, तो कहीं ना कहीं वो मिक्स कर जाएगा. ठीक है, तो यूजुअली दिस इज व्हाट हैपेंस व्हेन यू हैव वैलेंस बैंड, वैलेंस शेल ऑर्बिटल्स, एंड दे इंटरैक्ट वेल. सो द width of the band is large, each band, and they overlap with. So 3s and 3p band overlap, and that this kind of combined, you can view them combined band. Okay, so so we have already seen in case of magnesium कैसे होता है. So completely filled bands, both bonding and anti-bonding levels are completely populated. So this shading means completely populated, and partial shading like this means that it is filled up to this only, aluminium, magnesium. So sodium, in case of sodium, you have total of yes, 3s, 1s orbital can accommodate 2 electrons, and 3p orbitals can orbital 6 electrons. So when you are viewing the combined sp band, 3s 3p band, so each energy level, so there are 8 electrons that will be accommodated by interaction of 2. Okay. So only in sodium case you have only 1 electron in the valence shell, so only 1/8 of the band is filled. So this shading represents that for sodium only 1/8 of the band is filled. In magnesium case you have 2 orbitals per in the valence shell, and so the same number of orbitals have to be distributed, and electrons occupy them. So you have only 2 by 8. 2 by 8 times filling of the band occurs. In case of aluminium, there are 3 electrons per valence shell, so 3 by 8 filling of the. So 3/8 of the band is filled in case of aluminium. So this shading is done very carefully to illustrate that point. ये total अगर है तो इसका 3 by 8 part ही color किया गया है, not all. So that has been done shading has been done carefully. Okay, the energy difference between the highest level, so this is a gap. So top of the one band and the bottom of the upper this band, this is band gap. Similarly, any two bands if you compare, top of the higher energy band and sorry, bottom of the higher energy band and top of the lower energy band, this is called band gap, lowest level of the next, so like that. So this is the forbidden gap, forbidden energies, where no combination of atomic orbitals can exist. So each of the 3s and 3p orbitals, as I said, they are farther away from the nucleus. So the interaction will be good when the two atoms approach each other, and you have as compared to 4 levels, and the bandwidth is higher, so you will draw a very wide band for 3s and 3p. So the 3s and 3p bands are wider than the energy gap between them. So width कई बार इतनी ज़्यादा हो जाती है कि गैप से ज़्यादा width होगी. इंडिविजुअली आप 3s 3p बना सकते हैं, लेकिन वो ओवरलैप जैसे पहले शुरू के डायग्राम में भी दिखाया था कि ओवरलैपिंग अलग अलग शेडिंग था और ओवरलैप हो रहा. सो दैट रिजल्ट्स इन ओवरलैपिंग ऑफ द बैंड्स. So whenever width is greater than the gap, there will be overlapping bands, as happens here. So molecular orbitals derived from 2 or more valence orbitals are similar in energy. So the filling of bands, I told you how it happens. Combined band, so you have total capacity is 8 electrons per atom and 6 electrons. So that we have 3s orbitals has 6 electrons, can have maximum of 6, and each 3p orbital, 2 for 3s and 6 for 3p orbitals. So that's how we get 8. And then you combine valence band is 1/8 filled in case of sodium. Magnesium, it is 1/4 filled. In aluminium, it is 3/8. That filling has been shown. So this partial filled valence band is the key for conduction, already explained in the previous classes. So this availability of energy levels just immediately after the highest filled level, at very small energy, infinitesimally small energy above the highest occupied level, this is what ensures that electric conduction will be there. Very good electric conduction can be. So this is a diagram that illustrates the width of the bands. So 1s, you see, it is width is less. 2s थोड़ा सा और wide बनाएंगे, 2p, and then 3s So 1s, 2s, 3s. Nature of orbital is same. 1s, 2s are are formed. They are inertial orbitals which have been overlapping with the uh, atoms in the crystal, and these are bands are formed. So you can see that width is less. Idea is same as illustrated in previous. When you poor overlap gives you this kind of less width. Okay, so then we come to this another concept of density of states. So it may happen when we construct this kind of energy level diagram. For one given energy, you may have too many orbitals possible, different types of orbitals, degenerate orbitals that we say. So that for one given energy, so for given energy, how many such orbitals are available, that is known as density of states. It is expressed as density of number of energy levels, matlab number of orbitals in a very small range between E and E plus dE. So a very small difference when energy difference that we take, and number of orbitals per unit of energy within a band, or in a very simple way, if we like to say, then density of state is simply the number of orbitals for given energy within a band. So if the number is high, we say that density of state is high, or if it is less, density of state. So because of so E versus K relationship is parabolic. So what we expect here in case of a 1D metallic crystal, it will be highest near the bottom, and so the density of states will be highest near the bottom and top of the band. Okay, so where is the diagram? I will just so here so in this case, density of states for one dimensional crystal, highest near the bottom and the top. So bottom, and because the number of ways in which you can construct that orbitals is, and then it is less at the in the middle. So this is some, sorry, here density of states is like this. So this is for 3-dimensional curve actually. ये 3-dimensional का है. एक मिनट, 1-dimensional का 1 वाला कहाँ गया? Okay, 1-dimensional का ऐसा होगा. So number of ways in which you can construct, ये उल्टा चला गया. So for 1-dimensional system, we'll find that this is like this. Number of orbitals possible for this combination, and most bonding and most anti-bonding is more, and in the middle it is less. But if you go to the 3-dimensional curve, just iska ulta hoga. Compare 1D and 3D. If you look at it, it is just the reverse of that. In the middle you have maximum, and at the top, at the bottom, it is the least. So this is in the 3-dimensional case. So this is, there are more number of ways with which you can attain this orbital with this energy as compared to the most bonding or most anti-bonding energy. So situation is like you have x, y, z coordinates. You have a lot of, on this side orbitals atoms are there, on other side. So sorry. So there are more ways to make orbitals of n by 2 nodes here. So there here, if you are considering s orbitals, then you have no nodes here, and here you have n number of nodes, and here the number of nodes will be n by 2. So there are more ways in which you can construct n by 2 nodes as compared to 0 or n number of nodes. So this is like if you roll up 2 dice together, it is 6 plus 6, 2 6 लाना या 2 1 लाना सबसे डिफिकल्ट होगा, लेकिन बीच के नंबर्स लाना सबसे इजी होता है. तो 3-dimensional स्पेस में लगभग ऐसा ही होता है कि व्हेन यू हैव so many options are there, you will find that it is like getting 2 sixes or 2 1 with the 2 dice is very less probability, but getting any other number, like getting, if you choose number 5, 2 plus 3, 3 plus 2, 4 plus 1, like combination that you can work out is more. So there is only one way to make 2 or 12, but there's many ways to make a 7. So, because of that comparison tells you that in actual three-dimensional crystal, you have the density of states, number of combination possible for a given energy of in the middle is more as compared to the top and the bottom, the most bonding and most anti-bonding. And so electrons. So this was the original diagram, K versus E versus K, and now we are discussing E. On the y-axis you have the energy on y-axis in this particular diagram, in a density of state diagram, graph. This is the energy on y-axis, and x-axis you have density of states. So density of states here is maximum for the lowest energy, density of states is maximum for here, but when you go to 3D it is entirely reversed. So near the top of the band, dispersion curve deviates from the parabolic dotted line. This thing we have already discussed because of the periodic potential of the this atomic cores, the nucleus that you have. So alignment of the so in this case there is one top of the band, so deviation is there. One molecular orbital for each value of k, the number of orbitals per unit energy is highest at the bottom and top of the band for one dimensional chain. In two-dimensional crystal, it is almost in the middle. You have same for all this density of states is same. So in most of the time, what we are going to talk about, थ्री-डायमेंशनल क्रिस्टल का ही मेनली आपको डिस्कस करना है. आगे जो चल के सारा कुछ होगा उसमें थ्री डायमेंशनल को ही लेके ही हम सारा डिस्कशन करें, सेमीकंडक्टर, मेटल्स सबके लिए. So that profile is more important for you. So they are near the middle of the band. You have greater, and in the middle of the band, metallic. So one-dimensional crystal in real life, if you want to think of, this is the carbon nanotubes, which represent a one-dimensional system. In reality, three-dimensional crystals are more abundant. One-dimensional crystal, now we can talk about such things that is happening, like carbon nanotubes, and density of state for this is here. Okay. So this is another. So if you look at the density of states now for metals, in case of metals, this is S band, this is P band. On y-axis we can plot energy. On this axis, it is the x-axis. You have density of states, E plus dE. So density of states. So this is the kind of, so for three-dimensional crystal, you will obtain one this parabolic kind of thing, then another one for p orbital, and this is the, so you can, the gap is there between S and P band, but the S band, just in case of sodium or lithium, S band is half filled, so conduction will happen. So this is a typical density of state diagram for graph, density of state graph for metals. Then semiconductor and insulator, you have completely filled band, S band, P band is there, so empty P band, and there is gap. Gap hoga, completely filled band, separated, and you have another separated by energy gap with the other top P band. So half filled, then दिस इज कंडक्टिंग, इमीडिएट अवेलेबल हो गया ना। इसके बाद जो टॉप फील्ड लेवल है यहाँ पे, उसके बाद at infinitesimal energy you have next energy level is available, next orbitals are available. So this will ensure conduction, but in this case there will be no conduction at room temperature because of the energy gap. The top filled orbital has no vacant orbital available next to it at very at infinitesimal energy. So this is the distinction. जब आप draw करेंगे डेंसिटी ऑफ स्टेट्स डायग्राम, सो ये जो सेमीकंडक्टर में ये दो चीज़ें बहुत इंपॉर्टेंट है, ई वर्सेस के जो पहले बताया, और दूसरा डेंसिटी ऑफ स्टेट्स वर्सेस, तो दोनों तरह से आप बैंड गैप दिखा सकते हैं। और एक वो बॉक्सेस बना के भी दिखाते हैं, लेकिन वो ग्राफ नहीं है, दैट डज नॉट कन्वेज लॉट ऑफ इंफॉर्मेशन। बट इस क्या ई वर्सेस डेंसिटी ऑफ स्टेट्स, एक्स एक्सिस पे डेंसिटी ऑफ स्टेट्स यहाँ पे दिखा ना, ये एनर्जी है, और ये एक्स एक्सिस पे डेंसिटी ऑफ स्टेट्स, ये एनर्जी का स्केल है और ये डेंसिटी ऑफ स्टेट्स है। तो इसी यहाँ पे दोनों दिखाया गया, ई वर्सेस के, एंड देन ट्रांसफॉर्मेशन ऑफ द सेम थिंग कैन बी ट्रांसफॉर्म लाइक दिस। सो डेंसिटी ऑफ स्टेट्स, so mostly you will be encountering this kind of 3D for 3D crystal, metal, semiconductor, and semi metal is something which has slight just the top and bottom just overlap, slight यहाँ पे contact में, ये सेमी मेटल होता है। क्या क्या मेटल में यहाँ पे तो ये बैंड है तुम्हारा, और नेक्स्ट ऑर्बिटल यहाँ पे बिना एनर्जी, विदाउट एनी एक्सपेंस ऑफ एनर्जी इट इज अवेलेबल। हाँ ये तो शुरू से बोलते आ रहे हैं ना कि कंडक्शन, बॉन्डिंग से एंटी बॉन्डिंग नहीं, उसमें पार्शियली मतलब टॉप ऑफ द बैंड मोस्ट एंटी बॉन्डिंग, बॉटम ऑफ द बैंड मोस्ट एंटी बॉन्डिंग ऑर्बिटल है, बीच में सारे जो है वो पार्शियली बॉन्डिंग एंटी बॉन्डिंग सब कॉम्बिनेशन मिला हुआ है, ठीक है ना। सो हाँ, रिलेटिवली स्पीकिंग दे आर मूविंग टू मोर एंटी बॉन्डिंग कैरेक्टर, ऑर्बिटल्स, मॉलिक्यूलर ऑर्बिटल्स या क्रिस्टल ऑर्बिटल्स विथ ग्रेटर एंटी बॉन्डिंग कैरेक्टर, नीचे से ऊपर जाने में वो तो होगा, एंटी बॉन्डिंग कैरेक्टर बढ़ता जा रहा है, ठीक है। सो ये जो बॉक्सेस वाला डायग्राम है, ये भी इंफॉर्मेशन उस तरह की चीज़ों को दिखाने के लिए, बट दीज आर मोर सोफिस्टिकेटेड थिंग्स। ग्राफ अगर आप दिखाते हैं, सो सेम थिंग इफ यू ट्राई टू कन्वे सोडियम filled band and this partially filled band, this is like yeah, magnesium overlapping of the S and P, magnesium का केस, ये S ऑर्बिट S बैंड है जो partially filled है, this is the S and P with partial overlap, then graphite is here like this, so this is the total, and diamond which is having energy. So इंसुलेटर एंड सेमीकंडक्टर में बहुत ज़्यादा बैंड स्ट्रक्चर में अंतर नहीं होता है, गैप बस बढ़ जाता है, बस वही। कई बार उसको इंसुलेटर को भी हाई बैंड गैप सेमीकंडक्टर भी डिफाइन करते हैं। एटकिंस में लिखा है कि देयर ओनली टू क्लासेस, कंडक्टर मेटल्स एंड सेमीकंडक्टर, इंसुलेटर इज जस्ट टाइप ऑफ कंडक्टर, सेमीकंडक्टर वेरी हाई, आप बहुत हाई टेम्परेचर पे जाएंगे तब उसमें कंडक्टिविटी आएगी। सेमीकंडक्टर में रूम टेम्परेचर से थोड़ा सा भी हीट करेंगे तो कंडक्ट करने लगता है, उसमें भी होगा लेकिन बहुत हाई टेम्परेचर पे जाना पड़ेगा। सो गैप इज जस्ट हाई, सो दैट इज अनदर वे टू लुक एट इट। सो इन मेटल्स वी ऑल्सो द टॉप ऑफ द फील्ड, अगर ये पार्शियली फील्ड बैंड है तो द पॉइंट वेयर top of the field level is called Fermi level. So in this case, typically in alkali metals, the Fermi level is, so occupied levels, unoccupied levels, top of the level, top of this occupied levels is Fermi level. So n electrons, so half of them are occupied, and you have this highest occupied orbital is called Fermi level. So close to the Fermi level, you have unoccupied empty orbitals. So excitation is possible, and it will conduct electricity. So you have, so in the band theory you can explain this, because so there is no energy required to excite to the next energy level. Electrons are very mobile; they move to the next level and move throughout the crystal. They conduct electricity like that. So this is another view of, if you, suppose this is electrons being filled up. So middle of the level you have Fermi level, which has max. So in a 3D solid हमने क्या कहा था, halfway mark पे maximum density of states है, maximum. So for that energy you have several different types of combination of atomic orbitals is possible to give the same energy. So number of orbitals, molecular orbitals ज़्यादा है. So the view is something like this. So electron gas. So imagine like water is poured into a glass as given in the figure. So initially very few are filled at the bottom. So this is the situation when we are looking at the band density of state diagram in a 3D crystal. This is what happens. Then electron, these are, and finally at the top you have more and more water molecules, drops that can be accommodated. Similar thing is happening with the band structure here. When you are looking at sodium metal, you have less electrons in the lower for the lower energy levels, because the number of orbitals are less. But as you go to higher energy, more and more orbitals are available for the same, for one given energy, and in that case the number of, in each layer you will find more electrons in the, like that. So so top of this density, so this is the same idea that conveys density of states is proportional to e to the power half, and so there is a relatively large number of higher energy electrons in a electrons at in a given metal. So number of electrons out of the total electrons available, they have greater number of electrons which has higher energy in this particular model, है ना. मिडिल ऑफ द लेवल जैसे सोडियम में फिलिंग कर रहे हैं हम, तो वैसा अगर आप देखिए हाफ फिल्ड वाला जो इसका केस था, यहाँ पे अगर सोडियम मेटल के केस, so you have more electrons with greater energy, higher energy, and less electrons with less number of electrons with lesser energy is less. So this and this energy corresponding to this top field level is called Fermi energy, and you can also define the velocity of the electrons in that energy level. So that is, sorry, ये सबस्क्रिप्ट होगा. सिंपल आप हाफ एम वी स्क्वायर से काइनेटिक एनर्जी को इक्वेट करेंगे. हाफ एम वी स्क्वायर इज इक्वल टू, सो दैट्स अ सिंपल थिंग, लाइक लिखने में थोड़ा सा वो गलती हो गया. फर्मी एनर्जी के बराबर होगा, एंड और वी स्क्वायर विल बी इक्वल टू अंडर रूट 2EF, like this. So this, so we, so for we give a subscript here for Fermi. So electrons in the Fermi level will have this kind of distribution. Sorry, this is the velocity of the electrons. So it is, if you know the energy, you can calculate the velocity, and you can and this is the Fermi-Dirac statistic. We will talk about it later. Distribution of fraction of filling. So temperature dependence of the filling, that we'll be discussing later. We'll come to that. So top of the collection of electron energies, that is called this Fermi level, and the velocity is given by this, and the filling of electrons is they do not follow Boltzmann distribution, they follow Fermi-Dirac statistics. In this, that is slightly different. And these are so when fermions, so we know about electrons. अच्छा, अभी क्वांटम में हम गए नहीं है ना फर्मियंस पे. ओके, नहीं फर्मियंस मैंने बताया ना, हाँ बताया है शायद. फर्मियंस बताया ना, फर्मियंस बोसॉन्स अभी आपको नहीं बताया. सो जो हाफ स्पिन पार्टिकल होते हैं जिनका हाफ इंटीग्रल स्पिन होता है, सो इलेक्ट्रॉन हैज s इज इक्वल टू हाफ, वेयर्स फोटोन हैविंग, सो फर्मियंस एंड बेस, ये हम लोग आगे डिस्कस करेंगे. आई टोल्ड यू दैट like electrons, any fundamental particle has spin associated with it. So electron has spin quantum number s half, and you know the angular momentum. तो ये आपको बताया था कि स्पिन एंगुलर मोमेंटम इतना होता है, इससे एसोसिएटेड जो है. इसी तरह से फोटोन, इट हैज स्पिन क्वांटम नंबर फॉर s1, एंड दिस इज बताया मैंने जब एनर्जी ट्रांजिशन बताया हुआ, जब लैपोर्टे वगैरह बता रहा था उस टाइम बताया था मैंने, भूल रहे हो तुम लोग. अगेन सो इस तरह का, सो स्पिन का जो एंगुलर मोमेंटम वो फिक्स्ड है, उसकी वैल्यू द क्वांटम नंबर इज नॉट वेरिएबल. ठीक है, फॉर गिवन पार्टिकल. सो इलेक्ट्रॉन जहां भी होगा उसका एक ही मैग्नीट्यूड होगा स्पिन एंगुलर मोमेंटम का. इट इज नॉट, इसीलिए आपको कई सारी बुक्स में दिखता ही नहीं है क्वांटम नंबर, कहीं मेंशन नहीं होता है कई बार. ठीक है ना, आपको सीधा एमएस पे पहुंचा दिया था जो कि जेड कंपोनेंट अप और डाउन को बताएगा. आप वही समझते हैं कि एक ही स्पिन क्वांटम नंबर, ये कौन सा सर बता रहे हैं, तो वैसा नहीं समझिएगा. अब आप एस और एम एस जानते हैं. सो इसका जो जेड कंपोनेंट होगा, दिस, ये सब चीज आप जानते हैं ना. जेड कंपोनेंट इज गिवन बाय, इसका जो क्वांटम नंबर है एम एस, जैसे कल एम एल का बताया था वैसे ही. एंड the z component is given by ms, which can have plus s to minus s. ठीक है, तो ये प्लस और रादर राइट कंप्लीटली. ये आप बार बार बता रहा हूँ कि ये सब बहुत फंडामेंटल है और आप बार बार भूल जाएंगे, जैसे अभी भूल रहे हैं. बताया था पिछले सेमेस्टर में, लेकिन वो सब आपके दिमाग में रहेगा तभी आगे की चीजें. सो ऐसा जो बिहेवियर रहता है हाफ इंटीग्रल स्पिन, जितने भी पार्टिकल्स आप यूनिवर्स में डिस्कवर करते हैं, जानते हैं, उनको हम फर्मियंस कहते हैं. सो हाफ इंटीग्रल स्पिन, इफ यू, सो दो कैटेगरी में, ऑल द पार्टिकल्स इन द यूनिवर्स कैन बी डिस्क्राइब्ड, फंडामेंटल पार्टिकल दैट constitute the entire whole universe are described in two ways based on their spins: half integral spin fermions, and इंटीग्रल स्पिन्स जस्ट लाइक फोटोन, s इज इक्वल टू 1 या 2 3, इस तरह से इंटीग्रल मल्टीपल में जाएगा तो वो बोसॉन कहलाता है. सो दिस इंटीग्रल स्पिन, सो ये आगे अभी और आएगा, क्वांटम मैकेनिक्स में हम लोग करेंगे. इंटीग्रल स्पिन, दिस इज द इंटीग्रल स्पिन, पार्टिकल्स विथ इंटीग्रल स्पिन with it falls in the category of bosons. SN Bose, सत्येंद्रनाथ बोस के नाम पे है बोसॉन, so you should be proud of that. बोसॉन जो नाम है कैटेगरी, जेसी बोस नहीं, SN बोस, सत्येंद्रनाथ बोस. ठीक है, और ये जो दिस फॉल्स इन द कैटेगरी ऑफ, सो दिस इज हाफ इंटीग्रल स्पिन। जिस किसी भी पार्टिकल का हाफ इंटीग्रल स्पिन होगा, दे आर कॉल्ड फर्मियंस। सो इन सब का थोड़ा थोड़ा बदलता रहता है, डिपेंडिंग ऑन अ पार्टिकल इज फर्मियन और बोसॉन, बहुत सारी चीज़ें अलग है, बिहेवियर अलग अलग होता है। फर्मियंस के लिए ये हमेशा वो जो पॉलीज एक्सक्लूजन प्रिंसिपल, एनी फर्मियन विल ओबे दैट प्रिंसिपल, वो सिर्फ इलेक्ट्रॉन के लिए नहीं है, आगे चल के हम लोग क्वांटम मैकेनिक्स में ये सब देखेंगे। एनी फर्मियन विल ओबे दैट, एक्चुअली पॉली एक्सक्लूजन प्रिंसिपल इज विच जो हम इलेक्ट्रॉन्स के लिए करते हैं, वो स्पेशल केस ऑफ मोर जनरल पॉलीज प्रिंसिपल है, जो कि सारे फर्मियंस के लिए था। ठीक है, चलिए वो खैर अभी पढ़ा नहीं है आपने, तो इसलिए थोड़ा सा आगे तक, अभी हाइड्रोजन एटम में करेंगे तो इलेक्ट्रॉन्स का ट्रीटमेंट में वो सब आएगा। ओके, सो फर्मियंस, और ये मैंने बताया था फिर हाफ इंटीग्रल स्पिन, और आपका डेल्टा एल लेपोटे प्लस माइनस 1 क्यों होता है, इसी से उसी कॉन्टेक्स्ट में ये मैंने बताया था, मुझे याद आ रहा है कि फोटोन का स्पिन होता है। नाम नहीं बोला था कि फर्मियन क्या होता है, बोसॉन क्या होता है, लेकिन ये बताया था कि इसका फोटोन का स्पिन होता है। हाँ, ठीक है, और वो क्रूशियल है वो समझने के लिए कि लेपोर्टे में ऐसा क्यों होता है, लेपोर्टे रूल जो है वो ऐसे कैसे आता है, हाउ दैट इज ओरिजिनेट। सो इसको फर्मी सी भी कहते हैं, जो वहाँ पे एज यू सॉ इन दैट एनर्जी, the density of state is maximum in the middle, and if the Fermi level happens to be there, that is called the large number of electrons there with a given energy, so that is called a Fermi C. So they cannot so Fermi level is also defined as the surface of that C at Fermi C हो गया सारे electrons distributed in the sorry
आधा पर तो आ गया है, आधा पर कुलदीप लेके आ रहा है, तब यहाँ
अच्छा
बगलसरा पहुंचा है, 1 बजे तक वो आ जाएगा। ये सर ये स्पेक्ट्रोफ्लोरोमीटर में 2 केबल तो दिया था उसमें, 2 केबल सर और चाहिए।
तो लेके आएगा उसको दूसरा आदमी आने वाला जो है,
वो शायद लेके नहीं आ रहा है।
नहीं तो 2 केबल
यूपीएस का पार्ट है, 2 केबल दूसरे
ओके। सो फर्मी सी कहते हैं, और वो जो टॉप लेवल होगा फर्मी लेवल, दैट इज द सरफेस ऑफ द सी। तो वो जो हमने छोटा सा ऊपर एग्जांपल देखा था, इमेजिन दिस इज द electrons, you are filling this cup with electrons, so this is the sea of electrons, and this top level is the top of the surface is the Fermi. So this sea of electrons is also called Fermi sea, and the surface here is called Fermi level. So that was the okay. So Fermi energy will be very important for all these in describing the electrical and thermal properties of the solids. So they are almost around a few electron volts. Okay, so अभी आप गिरीश सर की क्लास है क्या? नेचुरल प्रोडक्ट्स है, अच्छा ठीक है, नेचुरल प्रोडक्ट्स। ओके, सो फर्मी एनर्जी इज फ्यू इलेक्ट्रॉन वोल्ट्स का होता है। okay, ripples. So ये जो ओनली जो सरफेस पे एनर्जी है, फर्मी लेवल पे जो इलेक्ट्रॉन्स है, मोस्टली वही एक्साइट होके ऊपर जाते हैं अराउंड द टॉप ऑफ द लेवल, बिकॉज बाकी सारे जो इलेक्ट्रॉन्स नीचे हैं, दे आर नॉट एबल टू रिसीव दैट एनर्जी। और एक्साइटेशन जो भी हम डिस्क्राइब करते हैं, डिस्क्रिप्शन देते हैं, आपको हमेशा यही कहा जाता है कि फर्मी लेवल जो टॉप ऑफ द लेवल है, वहाँ से इलेक्ट्रॉन नेक्स्ट लेवल पे जाता है। आप ये भी तो कह सकते हैं कि नीचे वाला, उसके नीचे जो इलेक्ट्रॉन्स है वो क्यों नहीं जाते, क्योंकि ये जो इलेक्ट्रॉन्स की एक्साइटेशन के लिए जो चाहिए, मतलब नीचे वाले के लिए थोड़ा सा और एनर्जी चाहिए होगा। सो दे नॉर्मल जो प्रोसेस है सराउंडिंग से एनर्जी जो लेके थोड़ा सा आपने इलेक्ट्रिकल कांटेक्ट दिया या हीट किया और वो हायर एनर्जी लेवल पे जाता है, वो सिर्फ ऊपर वाला लेवल, टिपिकल फिनोमेना दैट इज एसोसिएटेड विद द फर्मी लेवल, टॉप ऑफ द थिंग। लोअर लेवल्स दे विल, सो दैट फ्यू फ्रैक्शन जो उसका एक्चुअल एनर्जी कैलकुलेट करते हैं, सो दैट इज विद इन फ्यू इलेक्ट्रॉन वोल्ट्स, तो रिक्वायरमेंट है वो उसको मैच कर रहा है। पर इस केस में नीचे वाले के लिए एनर्जी लेवल, एनर्जी थोड़ा सा और ज़्यादा आपको चाहिए होगा, देना पड़ेगा। सो दैट यू सी रिपल्स ऑन द फर्मी सी जो आप, सो स्मॉल एनर्जी डेप्थ जो टॉप लेवल है, उसके एक दो लेवल ये जो तो उसको रिपल्स ऑन द फर्मी सी कहते हैं। इसको एक बार बाद में डिस्कस करेंगे, थोड़ा और डिस्कस करेंगे। हायर टेम्परेचर्स, इफेक्ट ऑफ टेम्परेचर ऑन द दिस इलेक्ट्रॉन्स के फिलिंग पे क्या इफेक्ट पड़ता है। So Fermi energy, we just calculated the velocity of the electrons in the Fermi level. The amount of energy which electron is given when you try to make a contact with a electrical positive and negative terminals. So वो few micro electron volts का उसमें जाता है। So electrons very close to the Fermi energy can participate and in the conduction process. Rest of the electrons do not. So this velocity is important. So velocity of electrons is highest in this case amongst all the electrons, set of electrons that is given to you. And so this conduction of electrons, conduction of electricity happens through this. So this is the Fermi-Dirac statistics that is applicable to this, all this thing. So this is Fe function, the probability that particle E will have energy E given by Fermi-Dirac. The terms that you see here, so this is the e to the power E minus Ef. Low temperature, these energy states, this is the Fermi energy and this is kT. So we are not using the Boltzmann constant here. Boltzmann constant is coming, sorry, here. But the typical Boltzmann distribution for e to the power g by energy by kT जो होता था वो वाला नहीं है. One, you are having a reciprocal of that. जो पहले हम लोग यूज करते थे बोल्ट्जमैन डिस्ट्रीब्यूशन फॉर अदर थिंग्स, उससे काफ़ी डिफरेंट है ये अभी स्टैटिस्टिकल मैकेनिक्स में भी ये सब आएगा. फॉर लो टेम्परेचर्स इफ दिस E is very very less as compared to EF, उस केस में क्या होगा, Fermi energy will have this will change to have, this will be like minus EF will dominate. If E is much less than EF, so this will become e to the power minus EF, and so the probability of particles having electrons, so this thing, so this this whole term, this will be almost very close to 0. So this is what happens at when the temperature is 0. Absolute 0 पे क्या होगा? Fermions will fill up all the available energy states up to level EF, called the Fermi energy. Okay. And of course the Pauli exclusion principle applies. At higher temperatures, above the Fermi level also filling starts. Okay. And this variation is then given by this statistics, Fermi-Dirac statistics. So variation with temperature higher when the temperature is raised above absolute 0. So that particular thing is called that filling is given by this particular thing. And some more thing about this temperature variation we can discuss later. थोड़ा सा और कुछ है, but I think it will continue with the temperature effects. Effect of temperature will be discussed in the next class. ठीक है, ज़्यादा हो जाएगा. जैसे कॉपर में इन केस ऑफ कॉपर 7 इलेक्ट्रॉन वोल्ट्स, फर्मी लेवल इज 7 इलेक्ट्रॉन वोल्ट्स, एंड द थर्मल एनर्जी हीटिंग का जो इफेक्ट सराउंडिंग से जो हीट होता है, केटी का जो 300 केल्विन रूम टेम्परेचर पे जो आप कंपेयर करते हैं ये 0.026 होता है. सो दैट इज समथिंग. चलो इसको नेक्स्ट क्लास में डिस्कस करेंगे, नेक्स्ट विथ सम मोर डिटेल्स about this.